Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 3 for this week, and going to attempt to take something that's actually very complex and simplify it as much as I can. But there is an equation in meteorology called the omega equation, and it's a diagnostic equation where it basically evaluates whether or not the air is going up or down. And there are two major components in that equation that contribute to whether or not the air is going up or down, and sometimes they cancel each other. One time you can have a really strong term that would indicate rising motion here, and the other term is very, very negative and completely wipes it out, okay? So you have to be really, really careful in terms of evaluating both of them together as opposed to just one or the other. So let me go on ahead and put myself down here in the corner. And I want to just talk a little bit about, it's just a little bit of calculus here, just to give you a feel for the kind of things that are in this equation, okay? And so this particular graph right here is of the function y equals 3x squared. So for instance, if x is minus 3, then you square that and it's 9. If x is plus 3, you square it and it's 9. And so you would end up with a value in here and a value in here, and it ends up being perfectly symmetrical right around 0, okay? And it's basically cupped like this. Now, one of the neat things, at least I think it's neat, about calculus when you start talking about derivatives, where the first derivative of a function, what you do is you take the derivative of that function and you calculate that, and that is the slope of the graph. And you remember how the slope is equal to the rise over the run? So for instance, from here to here, y is increasing and x is increasing, okay? So the slope would definitely be positive there. Over here, y is decreasing, but x is increasing, and so the slope would be negative in that area, okay? You can actually calculate an equation that will tell you what the slope is at any one given point. I'll get to that in just a second. And then the second derivative tells you the concavity of that function. Now, in here, you see how this is cupped upward like this? This is called concave up, all right? And so if the second derivative is positive, then the graph of the function is concave up. If it's negative, then it is concave down, and so it would be like this, okay? So that's what you can do with equations and derivatives and so forth. Now, how do you calculate a derivative? Well, you take the exponent, okay, times the number in front of the x, okay? So 2 times 3 is 6, okay? And then you reduce the exponent by 1. So 2 goes down to 1, and that's how you get the 6x, okay? Now, if you do that again to get the second derivative, the exponent here is 1, okay? So you take 1 times 6, you subtract 1 from 1, and you get 0, and anything to the 0 is 1, okay? So the second derivative is simply 6, okay? And 6 is a positive number, so you know that the graph is going to be concave up. And the second derivative basically tells you how the slope is changing, okay? So the first derivative tells you what the slope is, and the second derivative tells you how the slope is changing over time, okay? I hope that makes a little bit of sense. All right, so the omega equation, which again gives meteorologists a way of evaluating whether or not air is going up or down, and this is a very simplified version. I didn't want to show you the actual equation because it probably would have caused all sorts of panic attacks and all that. But basically, it has two terms, and the first one is the first derivative with respect to pressure. Okay, now we all know that pressure changes as you go up in the atmosphere, of vorticity advection, and we'll talk about that in just a second. So it isn't just the vorticity advection itself, it's how the vorticity advection is increasing or decreasing with height as you go up through the atmosphere, okay? And then the second one, that little doodad right in here, that stands for the Laplacian of the temperature advection. And what that basically means is, do you have a localized maximum or minimum, and it's very, very strong in a concentrated area and then quickly weakens as you go out from that area, okay? So the greater the change is between sort of the outside and where this localized maximum is or localized minimum, then the stronger the Laplacian is. Okay, so that's vorticity advection increasing with height, and that is a strong maximum or minimum of temperature advection. So what is vorticity advection, you ask? All right, so let's supposing we're looking at the upper atmosphere and this is the flow pattern, okay, where the winds are coming down from the northwest, and then you have the trough axis in here, and then the winds turn around and go back to the southwest, okay, or from the southwest. And then these red dotted lines here are equal amounts of vorticity. Now, the reason that the vorticity maximum is right in here, number one, is because this is where the maximum curvature is, okay? The curvature in the flow is going to contribute to a cyclonic rotation. And then the other thing is, if the winds are strongest down in here, and then they weaken up in here, if you think about it, supposing you had like a telephone pole like this, and the winds are blowing stronger at the bottom of the pole than they are the top of the pole, assuming this telephone pole is suspended in the air, it's going to start to rotate in a counterclockwise direction. So both wind shear and curvature in the flow both contribute to this being the area of maximum vorticity. So over here, the wind is advecting or moving higher levels of vorticity into this region here. So we call that PVA, or positive vorticity advection, which usually contributes to rising air. And then on the other side, you have NVA, or negative vorticity advection, which generally contributes to sinking air. But again, the omega equation tells us that we can't just evaluate that at any one level. We have to see how it's changing as you go up through the atmosphere. In the summertime, when the winds are many, many times weak, all the way up through the atmosphere, vorticity advection doesn't mean a whole lot, okay, because it's not changing with height. But in the wintertime, usually the winds increase quite a bit as you go up, and so the vorticity advection would definitely increase as you go up in the atmosphere. Okay, then the other thing is temperature advection. Now, these red lines represent isotherms, or lines of equal temperature, okay? And then these blue arrows are going to be the equivalent of isobars, okay? And you all know that the tighter the packing of the isobars, the stronger the wind blows, okay? So we have pretty wide spacing here and wide spacing over here, but very tight spacing here. And you notice that the isotherms and these isobars create little boxes here, okay? And so the smaller those boxes are, the stronger the temperature advection is, okay? So if you go from relatively weak, in this case, this would be warm advection because this is warm air, this is cold air up here, and the air is blowing it from warm toward cold. We have relatively weak warm advection here, but suddenly it becomes very, very strong here, and then it weakens again out here. So the Laplacian of the temperature advection is basically saying, or the higher the Laplacian is, the higher the value is, the more you have this really strong localized maximum of temperature advection, and then it quickly weakens on either side of that, okay? So if you have really, really tight packing of isobars in a fairly small area, and then those isobars aren't as tightly packed as you go out, the Laplacian of the temperature advection is going to be quite strong in that situation. Now, there are times where these two will cancel each other. Like for instance, you may have a big trough in the upper atmosphere approaching from the west, but a cold front has already passed. And so you have strong vorticity advection ahead of that trough, but you're in strong cold advection because the front has passed and the cold air is pouring in. In that case, the two cancel each other and you don't get much of any vertical motion, either up or down, okay? But if you have a situation where you have a trough approaching from the west and you've got warm advection going on, say ahead of a cold front, then the two add up up, and it can generate very vigorous upward motion in that kind of a situation. And a lot of times tornado outbreaks will occur in situations just like that. I hope that makes at least a little bit of sense. It basically says we look at vorticity advection and temperature advection, and we see how the vorticity advection is changing with height, and whether or not the temperature advection is very strong in a localized area, and then it quickly weakens as you go out away from that area. Those are the two main contributors to upward or downward motion in the atmosphere. All right, that's bonus weather video number 3 for this week. And the next one, of course, will be coming up on Monday, and the next daily weather update coming up on Monday as well. So have a great weekend, everybody, and we'll talk to you then. See you later.